Well, in this series, I shall briefly recapitulate what I had taught in the previous lecture, and then I will go ahead further on. So let us just recall what we had taught in the previous lecture. Okay. In the previous lecture, we had seen what are known as spatial and planar open chains. Spatial and planar open chains. This we had looked at. Now, the degrees of freedom of these open chains, how many degrees, what are the types of joints which are used, open chains. Okay. Now, we notice that we are using some R, P joints, that is the revolute and the prismatic joints, because these can be powered. That is what we had seen. Moreover, we notice that the axis can be parallel or perpendicular to each other. This is what we had seen. This is what we had seen in the last lecture. Okay. As we go on, we will see much more about details about this. We have also seen what is known as the direct kinematics, where if the joint angles are given, then you know where the end effector is. That is what we have seen. Also, we had briefly looked at what is known as inverse kinematics, where if the end effector position is given, you know what the joint angles are. Inverse kinematics. These are what we had seen in the last lecture. In addition, we had seen what is known as resolution, accuracy, and repeatability. The most important of these is the repeatability, because whatever your robot does, if it repeats continuously without error, you are very happy. Accuracy, yes, more expensive robot used in very small workspaces, you do need accuracy. Then the resolution, what is the minimum distance the end effector can go, because that depends on the resolution of the various elements. Also, links are subjected to forces, consequently they bend, there is backlash, all these decide all these parameters like resolution, accuracy, and repeatability. We had seen that also. Okay. We had also looked at the workspace. We had seen that in a Cartesian robot, the workspace is some sort of a cube, and we had seen that the system occupies a lot of space. That's what we had seen. Yesterday there was a question after the lecture. Some student asked me a question, so I will briefly touch upon it before I go over to what I am going to discuss today. Okay. Now let me look at that. You see, yesterday the question was very simple. Yesterday what I had told you people was this. I had taken a Cartesian robot or something like this. Okay. And then I had said that the workspace of this Cartesian robot is fairly not as much as one would desire in comparison to the overall size of the robot. That's what I had said. So the student was asking me, sir, I am not very clear about that. Could you kindly look at it again? So that's why I am just visiting that and looking at it again. Now let me draw a Cartesian robot here. I have got this, and I have got one joint like this. I have got the prismatic joint here, and I have the gripper here. I hope it does look like a Cartesian robot on this. Okay. All right. Now I can drive this axis through various means. I am using a pneumatic cylinder here. Here is a pneumatic cylinder which powers this axis, the motion of this block. So this motion is obtained by this cylinder of the whole block. Up and down motion may be something else, and the inward and outward motion of the gripper. So when you have a pneumatic cylinder like that, let us say the cylinder length is L. See, I have this pneumatic cylinder. There is a piston in it, and then if this cylinder length is L, the stroke is also approximately L. So if the pneumatic cylinder moves in and out, and you get a cylinder length of L, overall space occupied by the pneumatic cylinder is 2L. Now if I have a workspace here, which is L into L into L, and I use 3 pneumatic cylinders, one for the X motion, one for the Y motion, and one for the Z motion, then the overall space occupied is 2L into 2L into 2L. That's what I mean. Whereas the work volume is only L into L into L. Now, if you use a screw like in a lathe for the feed, for cutting, you move this way and that way across, you use a screw. Now, if the stroke is L, you want to go a distance L, right, from this end of the lathe to the other end, then the overall length is also somewhat similar to L. But there will be a motor, gearbox, and that position, so maybe 1.5 times L. So then you will have to multiply, if you use screws for this, into 1.5 L into 1.5 L into 1.5 L will be the overall space occupied, whereas L into L into L is the. Now the next question that comes up is, can you conduct a similar exercise for this, what you call that, spatial manipulator of the articulated type? That's what. Can you conduct a similar exercise? Now remember, when you stretch these two will line up and you will get a length of L1 plus L2. This is L1 and this is L2. You will get that total length. When you fold it, this will come somewhere here. If L1 equal to L2, this point will obviously come to the center of this. So can you conduct a similar exercise? This is just to give you a feel of the workspace and relation to the overall system size. You can add a wrist also. Once you add a wrist, what will happen is there are many things, the workspace, the way you look at the workspace changes once you have a wrist there. So I have this robot, okay, I have the main link, main body here, then I have one more, and then I have added a wrist here, and put the gripper somewhere, gripper or end effector. The correct terminology is end effector. I tend to use the word the gripper. Now when this folds and comes here, then that length, let us say this is L1 and this is L2 and this is L3. The distance from the center will depend on whether this fellow is in line. These three are, if these three are in line, you can fold this back here, you can stretch it out. The outer edge of the workspace will be when all these three are stretched out. But when you bend this also, you get, or when you bend all of them together, what sort of a workspace will you get? And what is the relation? Have a look at it. Just examine. Now these are things which we would like you to do it on your own. So there is of course the vertical axis. The whole thing is swept all around. Okay, that's what I was telling you yesterday when I talked about the workspace and the relative sizes of the system as in relation to the workspace. Okay, so now having spoken this, let us go ahead with what are known as closed chains. These manipulators with closed chains are becoming quite important in manufacturing in particular. What we call as closed chains. You had seen so far the open chains. Here is an example of the open chain. Again, this is a spatial open chain. We had also seen examples of planar open chains. Okay. Now we will see what are known as closed chains. I will begin with a very simple, what you call that planar open chain. Now planar closed chain, the simplest planar closed chain I can think of is the planar 5 bar. I will call this, I will name it A, B, C, D. It's a 5-sided figure, right? A quadrilateral is 4-sided. I won't call it a pentagon because that's a special 5-sided. I will call it a 5-sided, 5-bar chain. You can count 1, 2, 3, 4 and the fixed link as the 5th. And you can see there are revolute pairs. I could have prismatic also, but I have right here revolute, revolute, revolute. Here also a revolute, here also a revolute. So I will call it a 5-bar closed chain. 5r, the dash is not a subtraction, that's a 5r closed chain. I think actually I should remove the dash and simply write it as 5r closed chain. This is what it is. Now the question is, how many degrees of freedom does it have? There are formulae which we will give you. Is there any other way of doing it? That's the question we ask ourselves. I have fixed this link. AE is already fixed. Once I have fixed this link, how many degrees of freedom does it have? Try to draw the 5-sided figure. Now let's say you fix this link. Okay, if you want to draw a quadrilateral, there are 4 lengths available to you. Can you draw it? Just be given 4 lengths a quadrilateral. What else additional information do you require? You need one angle. So now it is a 5-sided figure. 5. So what else additional? I just give you these lengths AB, I give you BC, I give you CD, I give you DE, and I give you AE. Now I ask you the question, draw it. Now what additional information do you require? You need 2 angles. Unless you are given 2 angles, you cannot complete the picture. Okay, so it's a 2-degree freedom system, because these are all given to you. Now is there a way of finding out what are the number of degrees of freedom given something like this? In theory of machines, you have a procedure which is known as the group. You all recall, it's called the I hope I have got the spelling right. Yes. No, I am sorry, there is no R here. Gubler. It's called the Gubler. Okay? Now, those of you who are mechanical engineers are familiar with this formula, but I will simply touch upon it, because we need it even in the spatial closed chains. We will need a similar formula. What the formula says is that given a set of n links, number of links, okay, J suffix R is number of revolute pairs, all in the plane. I am writing the formula for the planar case. Revolute joints, then Jp is the number of prismatic joints. When you connect 2 links through a revolute pair or a revolute joint, how many degrees of freedom does this link possess with respect to this? 1. If I give this angle, you know where this link lies. So, in a plane, how many degrees of freedom are there? We know that there are 3 degrees of freedom in a plane. So, if this is one plane and this is another plane, okay, with respect to this, as long as these 2 links are free, they have 3 degrees of freedom relative to each other. But the moment I have put this revolute pair, you have lost 2 degrees of freedom. Lost from 3 available, in a plane. Okay? That is when I put a revolute joint. Same logic applies to the prismatic joints also. You lose 2 degrees of freedom from a prismatic joint. When I fix this link to something, to another link, how many degrees of freedom do I lose? When I fix it in relation to the other one. I fix these 2. I paste them together, glue them together. How many degrees of freedom? I have lost all 3 degrees of freedom relative to each other. So, when I fix 2 joints, when I fix 2 links to each other, I lose 3 degrees of freedom. When I pivot one link through a revolute joint, I lose 2 degrees of freedom. When I connect 2 links through a prismatic joint, I again lose 3 degrees of freedom. So, what we do is, in any mechanism when there are n links, you have a total of 3 into n degrees of freedom available to you, but you usually fix up one link, that is a reference link. So, you end up with 3 into n minus 1. And each revolute pair removes 2 degrees of freedom, so I lose 2 into JR, and each prismatic pair removes 2 degrees of freedom. This is the formula. Let us apply to the 5-bar linkage which we had drawn. There are 1, 2, 3, 4, 5 links. One is fixed, so n equal to 5. One of them is fixed, remember that. So that is taken care of by this minus 1. Then there are 1, 2, 3, 4, 5 revolute pairs, JR equal to 5. So when I multiply 3 into 5 minus 1 minus 2 into 5, I get that's the number of degrees of freedom available. That is the number of degrees of freedom available. So the formula also gives you the degrees of freedom, but you can also find the degrees of freedom by drawing. One of the reasons why I keep repeatedly telling you to draw it is, it gives you a feel, how many angles do I require to draw this picture? That's a number of, because all the lengths are given, remember that, provided the lengths are given. Okay, this is a closed kinematic chain. I could replace these revolute pairs, all these here, in this particular case all are revolute pairs. I could also have one with prismatic joints. I will show that just for the sake of the number of links are, the base link is 1, the same base link is there. The guide is also a base link, remember that, part of the base link. So that is numbered 1, this is 2, this is 3, this is 4, and the fifth link is this slider. The slider is also a fifth link. There is a joint between 5 and 1, that is the prismatic joint. There is a joint between 5 and 4, that is the revolute joint. So I have R here, R here, R here, but I have a P here. So 1, 2, 3, and there is an R here inside. Here between 4 and 5 there is an R. R. Between 5 and 1 there is a P. So here also number of links is 5. The number of revolute pairs equal to 4. The number of prismatic pairs equal to 1. And this can be here also. I can replace this R with a P and I will get some other figure. So these are known as parallel manipulators. And these are planar ones. I have so far looked at the planar. Okay? In any one of those links, in this parallel manipulator, one could mount his end effector. For example, let me go back to this particular picture, and I could mount the end effector here on this link. They are stiffer than the serial chain. The serial chain tends to hang, series of links. In a serial chain, you have a series of links like this. Only one like that. So when you apply a force, something tells you this can withstand the forces better than this, right? Here the motors have to, because you have got two things parallelly coming and holding on to the, supporting the end effector. In this case, two parallel paths to the end effector to the ground, whereas there is a single path here from the end effector to the ground. So this tends to be stiffer. Though the work volume of the parallel chains is not as much as that of the serial. The work volume available. That's one of the problems. You could of course have a serial. If you have a 2 degree of freedom system, can you orient the end effector in any direction you like? when you have 2 degree of freedom planar system, can you orient the end effector whichever way you like? In a plane we require 3 degrees of freedom system, so we should go for a 3 degree of freedom system, closed chain. I will draw one, may not be the best in the world, but nevertheless 1, 2, 3, 4, 5 and 6. So this is link 1, link 2, link 3, link 4, link 5. So let us write the formula. 3 into n minus 1 minus 2j revolute. We don't have any prismatic, so I leave it here. This is the degrees of freedom formula. N equal to 6. How many revolute pairs are there? Are 1, 2, 3, 4, 5. So JR equal to 6. Am I right? Check. 3 into 6 minus 1 minus 2 into 6 equal to. So this guy can orient an object. Supposing I put my end effector here. Not only can you position him where you want, but again remember the workspace here is considerably smaller than what you get in the serial chain. It would be instructive if you could work out the workspace of the 5R planar chain. You just try to work out by drawing the workspace. How will you know where the boundaries of the workspace are in the case of the 5R? Where are the boundaries of workspace? Boundaries of workspace. Just like in the case of a Cartesian main body of a serial chain, we could find the boundaries of the workspace. Can you find the boundaries of the workspace of this planar chain, the 5R at least? Try it for the 5R. Also, we had looked at this problem of number of possible orientations for a given position. Can you look at that? Parallel, I will just write here. Chain 5R. Can we find workspace boundaries? Right? Then 6 bar closed chain. Okay, remember that. Number of orientations. Or rather I should use the word range of orientation. Range of orientation, that's a more appropriate word, not number. Range of orientations for given position of end effector. Now, will it change in the workspace? These are the questions one has to attempt to answer. This is a planar case, remember that. I think these are the questions one should attempt to answer as he goes through. I would like you to try it out on your own and get a feel of the workspace and other of this system. It is not very difficult actually to work out this. Use your compass and pencil and do that. Yeah, you assume. Assume the ranges of motion. Sometimes it may lock up also. Link length also. Assume a set of link lengths, assume the ranges of motion. Sometimes that's the reason why I am asking you to do the exercise. You will suddenly find that you can't go beyond a particular point, depending on the choice you have made. Use a compass and a ruler and do it. Okay, so that is as far as the parallel planar chains are concerned. We will have a look at the, we have seen the Gabler's formula for the planar chain and seen this. Now let us just look at the direct and inverse kinematics. Just a feel of that also. Okay. Direct, inverse. I will give you a feel of this here also. Now direct kinematics of the 5-bar planar chain, 5-bar planar closed or parallel, I can use both. In the direct kinematics, what do we say? The angles are given and you have to find the position of the end effector. Let's try to draw it. Link lengths are given. That is assumed. So link lengths are given. Link lengths are specified. That is the correct word I should use. Specified. Angles are given. Are given. Find where the end effector is. Position of end effector. I will call it E, not electrical engineering, end effector. Okay. So what do you do? How do you go about? You first will draw the base link. Then you are given the two angles, so you will draw this link and this link at this angle. Then the other two link lengths are known. Now you will put your compass here, draw one arc, put the compass here, draw another arc, and you will get two possible assemblies of the fiber. This is one assembly, other assembly will be. I am sorry, I didn't draw this circle properly. One circle will be, I will draw it again on another sheet. So I am given the base, I have drawn the base. I have drawn the two cranks. One is here. This angle is given to me. This particular angle is given. So I draw the other crank because the other angle is also given to me. Then I put my compass here on this revolute pair. Draw a curve like this. Circle. Then I put my compass here. Take that corresponding link length. Draw another circle. So I get two intersections. So I can assemble this phi bar either this way or okay, I call it two modes of assembly. That is very important. We can figure out can it switch from this mode of assembly to that during motion. That's one of our concerns. We'll have to find out. Can it switch from this mode? This is, let's call this mode 1 to mode 2 during motion as you rotate these two inputs using a servo motor. Can it? Maybe not. You figure it out. But these are two modes of assembly. Okay. Now comes, this is the direct kinematics. Now let's go to the inverse kinematics quickly. Have a brief look. What is it in inverse kinematics? The position of the end effector is given and you have to find the angles. All the link lengths are given. Inverse kinematics. Link lengths are specified. Link length specified. Okay, and what else is specified? The position of end effector is specified. Effector. When I say position, I use the word very loosely. Actually, what I mean is both the position and orientation. Is given. That is, I should say more clearly, the location of the end effector with respect to the base of the phi bar. Now you have to do that. So, will it be, in the case of open chain, we saw there are multiple solutions, multiple ways you could reach, right? Would it be similar here? Figure it out. Use a compass and a pencil and do it. I mean, see, these are things if you do with a compass and a pencil, it hardly takes any time to draw a few of these pictures and get a feel of what happens. That is very important. You can't do it for a 3D. The spatial manipulators, it's very tough to draw, use a pencil and a compass and a ruler and figure out all these things. But it pays. It enhances your understanding if you do it for the planar. I suggest you do it. Select your own link length. You may do it for the 5 bar or you may do it for the 6 bar. Specify, draw it, and then try to figure out what is going on. what I would like to request you to do. Okay. So now we have seen the planar 5 and bar closed chain as well as the 6 bar closed chain. The 5 bar closed chain allows you to position the object. The 6 bar allows you not only to position but also orient, because it has 3 degrees of freedom. Let's go to the spatial one. That is let's just look at the spatial. I will draw the spatial manipulator. It is known as the Stewart platform. Platform, FORM. Now this has been used, the Stewart platform. I will sketch it here. You can also slowly sketch whatever I draw. Essentially, Stewart platform consists of two, what you call, discs, one at the top, one at the bottom. There is a disc at the top and there is a disc at the bottom. These are connected together. There are two discs and they are connected together to some linear actuators. I am showing the linear actuator here. This could be a ball screw driven by a motor embedded inside the actuator, or it could be a hydraulic or pneumatic cylinder. Typically, the hydraulic cylinder is used. Now, here is the linear actuator. Two linear actuators. This is the piston rod coming out. This is the cylinder. Two. You notice this particular linear actuator is pivoted to the bottom. Here. You see this one. And pivoted at the top. We will see what sort of joints are used. They are not the conventional revolute. This is something else. I will come to that. Let me complete the picture first. Here is another actuator. And this fellow is also pivoted here in some form. There is another actuator. So you see two pairs, two actuators. At the top, both the piston rod ends are connected to a specific joint on the top disc. At the bottom, they are separately connected. Okay. This is a ball and socket joint, a spherical joint. I will call it S at the bottom. What is known as a spherical joint is used. So we have, right now I have shown 4 actuators. There are 2 more. There are 6 actuators in all. 6 degrees of freedom in the space. So you will essentially need 6 actuators. Okay. These are there. Now there is one more here. Again this is connected and this is two. You got the picture now? Reasonably fine. On top of it I have kept a drill, motor with a drill on it. In the end effector there is a motor with a drill. Imagine it's a drill. Now the top plate can tilt and move with respect to the bottom plate as these actuators are actuators. There are 6 actuators. These 6 actuators, as I said, are connected to the bottom plate through spherical joints, the ball and socket. At the top, they are connected through hook joint. All of you are familiar with the hook joint. The hook joint is found in automobiles. Let me draw a. Okay, the hook joint is found in automobiles. You can, while you are drawing that, sketching that, I will just briefly sketch the hook joint. How many degrees of freedom does a hook joint have? The hook joint has how many degrees of freedom? No, just think. You have seen it in the automobile. How many? 2 or 3? Are you sure? Not very sure. See, here is a hook joint. Let me put that paper on top and show you the hook joint. It's a very tiny one. Okay. Now this rotation is possible. Also this is possible. That's all. This is not possible. There is play here. Otherwise this rotation is not possible. So how many degrees of freedom does it have? This one rotation of this with respect to that. Okay, one rotation. Okay, right, and the second rotation. Only two are possible. So how many degrees of freedom? So let me show you the Hooke's joint. While you are sketching the Stewart manipulator, I will draw the Hooke's joint here. Now any automobile shop will give you a Hooke's joint if you go and ask them. Okay. It's a 2 degree of freedom. Here I have got a picture of the Hooke's joint. I hope it, the star like thing, you know, 4 across, you know, you have a cross and one side of the cross you hold like this, the other side of the cross. There are 4 revolute pairs in it, the way it has been shown. I am sorry, though there are, it's not 4, it should be called 2 actually, because you know 2 are in the same axis. It's like a door, you don't have a single hinge, you have one hinge at the bottom, one hinge at the middle and one hinge at the top. It's still only one revolute pair between the door and the wall, so something like that. There are 2 revolute pairs, I shouldn't have said 4. So this is the Hooke's joint. So in space, how many degrees of freedom does it have? 2. How many degrees of freedom are there in space? 6. So how many are removed by this Hooke's joint? 4. A spherical joint has how many degrees of freedom? 3. Okay, in space there are 6 degrees of freedom, so a spherical joint removes 3 degrees of freedom. So using this knowledge and using the same equation, we will have to rewrite the Grubler's equation. Shall we rewrite? Let us see. We will rewrite. Now how many n equal to number of joints. So we will write this. Let me just adjust this. N equal to number of joints. I am writing the Grubler's equation. N equal to number of joints. We will count that. I am sorry, number of links. I am extremely sorry. We will count the number of links. Don't worry. Js is the number of spherical joints. Spherical joint. Alright. Js we have got. What is the other type of joint we have used? The Hooke's joint. We will call it Jh. Number of Hooke's joints. Alright. That clear? Number of Hooke's joints. Jh. So shall we write the formula now? Now we are working in space, remember. So we had 3 into n minus 1 as the first term of the degrees of freedom equation in a plane. Now how much do we have here? 6 into n minus 1. So we will write 6 into n minus 1. A spherical joint removes 3 degrees of freedom. So 3 into Js. And a Hooke's joint removes, so it is 4 into Jh. Number of, okay. Now let us work it out for the, are there any other, now what about the revolute joints? How many do they remove in space? A revolute joint has 5. So minus 5 into J revolute minus 5 into J prismatic. This is the entire formula. There are, if we, depending on the joints, you know, this is for the degrees of freedom in space. Let us apply it to the Stewart platform. Let us go back to the Stewart platform and apply it here. How many links are there? Let us count. It is always better to write the link numbers on the drawing itself. There is the bottom plate, there is the top plate. So I will call this 1, I will call this 2. Okay? What else? there is a link connecting the piston to the top plate. Piston and the piston rod is one link. They are connected through a prismatic pair to the cylinder, right? Cylinder and whatever is the mounting of the cylinder is another link. So we have one more link here. We'll call it 3. We'll call it 4. Fine? Is it okay? Now can you give me the number of links? 12. See, there are 6 cylinders. In the cylinder there is a piston and a this one. So that will be 12 plus the top plate and 14. So n equal to 14. I hope the formula works out, otherwise we will be in trouble. So it will be 6 into, so n is 14. What about the number of spherical joints? There are 6 here at the bottom. So I will call Js is equal to 6. What about the number of Fuchs joints? Again 6. No. How can you have? Just because you have, see, let's say in a window, I have connected this here. I have a revolute joint here, right? I have connected another here. I have another revolute joint here. To you, how does it look? See, supposing this is, I'm sorry, I should have had one more here. Okay, let me draw it here. Let me draw it and show it to you. See, I have got one link. I have connected one more link here, and it can rotate through a revolute pair. Okay? Then I have collected one more here also. One more. It's better to draw it with the complete this. Okay. These two are connected together. Then one of you comes and says, no, one more link I want to add here. So he connects one more link. So there are 3 links here. 1, 2, and there is what appears to be a single revolute pair. Actually, there are 2 revolute pairs. One connecting, accommodating the relative motion between 1 and 2. There is one revolute pair. Another accommodating the relative motion between 1 and 3. There are 2. Similarly, here in the Stewart platform, the piston rod of this is accommodated, connected to the top plate through one Hooks joint. The other piston rod is also connected to it. So there are 6. Are there? Have we exhausted? Have we counted all the joints, or is there any more joints here? 6 prismatic joints. Now you see whether the formula works. If it doesn't, then we are all in trouble. Something is wrong. Then let me go back to the formula. I have the whole thing here. How many degrees of freedom? Prismatic is 6. Oh, sorry. Prismatic is 6. So how many degrees of freedom is it coming to? 14 into 6 degrees of freedom. Okay. This Stewart platform is used in the so-called aircraft simulators. You have heard of the aircraft simulator, where the pilots are trained? This is the device. All 6 cylinders are moved in certain fashion under computer control, and the pilot gets the feel of the aircraft banking or diving or going up. Of course, the accelerations, I don't know whether you can really feel them. When an aircraft really goes, you have so many accelerations and velocities as aircraft. Those may not, but to some extent maybe yes. But generally, this is what they use for. Nowadays, it has become very important because by mounting drills, you have in your machine, what you do is, you have the Stewart platform sticking out like this with the drill bit, and it keeps going this way, that way, drilling holes in several orienting. These fellows are very, very stiff. So many connections to the base from the floating link. So it is very stiff. And instead of hydraulics, you can use the ball screw. So all electric Stewart platform. Remind me to show you a picture of that in motion. I forgot to fetch it today, but in one of the next lectures I will show you that in motion. The Stewart platform in motion. This has become a very popular in machine tool originally conceived for aircraft, then now machine tools. They are using this. Grinding, making dies, all these things. The tool may be carried on the steward platform top plate, or the job may be carried and the tool may be grinding, for example. Sometimes the tool will be grinding, wheel will be spinning, and the platform will tilt things like this. So that is what is known as the steward platform. So we have seen the steward platform, the hooks joint. I hope I have covered that. Okay. So now we have seen what are known as serial manipulators, what are known as parallel manipulators. In the process, we have looked at ways and means of finding the degrees of freedom by counting the number of links and number of joints. Remember that degrees of freedom equation is simply a counting. You have to be very careful. You have to number on the links. Don't forget the fixed link. Usually that's what you do. Particularly if the prismatic pair is on the fixed link, you simply tend to forget about it. You don't count the slider. These are the typical mistakes students make. But once you get the hang of it, there is nothing big. So this is what I just wanted to do. So we have now a fairly good idea of the various kinematic structures and some of their properties. We have also learned something about inverse kinematics, direct kinematics. We have seen the degrees of freedom. Some idea of industrial manipulators you have in your mind before we go to the advanced topics. There is one more thing I wanted to. I will pose it as a question to you. A robot is sitting here on the table. It's a planar robot. This is the one you have. Okay, there is an end effector, and somewhere here there is an object sitting like this. Okay. Now remember, how many degrees of freedom does this planar robot have? 3 degrees of freedom. Now, can I find out the position and orientation of this object using this fellow robot? That's the question I have. Can I use the robot as a measuring device? Can one use robot manipulator? I use the word robot manipulator. That's a more appropriate word. Don't call everything a robot. Robotic aircraft, robotic manipulator, robotic ship, that will be a better word. Robot manipulator, robot fish. Robot manipulator as a measuring device. What do I want to measure? The position and orientation of the object. The question, that's the question. Answer can be yes, no, or no opinion. I don't know which answer you want to give. Yes. What I do is, I pick up the end effector of the robot and bring it, and I do this. I match the end effector with the object. I keep taking the end effector and match it with the object. The object is stuck on the table like that. Then what do I do next? I know the link length, because when you have given me the robot, you have given me a robot with a definite link length. These don't change. They are fixed. They are known as link parameters. The word we use for link length is link parameters. They do not change given a robot. Anything, any dimensions of links, etc., or even the angle between links. I said the axes are parallel, the axes are perpendicular. The angle between one axis and another could be called a link parameter, because it doesn't change during the motion of the robot. Okay, whatever changes, the angles that change as you move the robot, at the joint angles that change, they are known as motion parameters. You will slowly start using these words rather than in a prismatic pair. If a prismatic joint is used, then the linear motion of that slider is a motion parameter. Motion parameters and link parameters, these are some of the terminologies one should know. So I can use a robot as a measuring device, since I know the link parameters, and I can measure the motion parameters through what? Through the encoders or the potentiometers here. So once I know that using trigonometry, I can tell you where this particular object is. It's a very important thing, you know, because you may be scratching your head and trying to figure out where the object is. You will say, I'll put a camera and all that, and somebody comes and just puts this and says, I'll read the encoders and get the information I want. Okay. So now remember, once you have matched this, are there multiple or only one? Once you have brought physical robot is there a unique set of angles or are there multiple? The physical robot has been brought here, remember, unique. It's only in the equations you get those multiple solutions. When you have brought the robot like that physically and matched it with the object, you have positioned it yourself, so these angles are unique. Whereas when you solve the equations, you will find, that is when you draw, construct and all that, you will find. But when you have got the physical robot sitting here and you bring it, you have got a unique set. So I can capture the information of all the objects on the table simply by using the robot as a measuring device, and I can say that for this particular object, these are where it is. I can write the XYZ coordinates, or I can simply write these three angles. Correct? I need not do anything more. I can say that after the measurement is complete, I could write object 1 x, y, comma, gamma. Gamma is the angle of orientation, if you recall. Yesterday I had used the word gamma, okay, as the angle of orientation, remember? With the x-axis, I will say gamma is the angle of orientation. This is my definition. You can define it the way you want. The positive x-axis, anti-clockwise positive, gamma is the angle. So object 1, I can list down xy gamma, or I can write down theta 1. How many angles are there? But this information has to be used along with the link parameters to arrive at this. So object 2, I can use the same robot to figure out where that is. Find this xy gamma, or again I can make a table like this for each object. Now I don't have any sophisticated vision or anything. Just using the robot itself as a measuring device, one can do this. We'll worry about that later. You worry about that later. Why should I say we will worry about that later? You worry about that. Can we do it with a closed chain? Okay, that's a nice question. I can capture it for the examinations, you know, quizzes. Can we do this with a closed chain? Any? Remember, the physical robot is there. You are not drawing it. You must keep that in mind. With a, okay? Remember that. You have got the physical system, you can build using a Lego set like I did, you know, you can build it. Using cardboard, you build it and then you figure it out. Do that with the physical system, not with a pen and pencil and all that. You can get the feel with a pen and pencil, do it. Because you have the robot sitting in front of you, link lengths are known with a parallel manipulator. Correct? This is the question you have asked me. Good. You figure it out. If I tell you everything, I won't have anything to ask you for the exams, right? So, right? Of course, sometimes I may not know the answer, so I can get away by saying you answer it. Okay? So, this is one way of doing things. Now, these are some of the terminologies which we have to, I'll introduce a few more terminologies. Some of the terminologies which you will require as you go along. There is a table on which some objects are sitting, and the robot is also sitting on the same table. Again planar, just for the sake of understanding. Okay? We call this the world of the robot. We call this the world of the robot, WORLD. It's a table only. All the things the robot wants are there. The objects it has to pick up, tasks it has to do. So that's the world of the robot. Now, the robot is fixed somewhere in this particular table. Okay. So if somebody comes and asks me where is the robot fixed on the table, I would like to tell him. So obviously, what will I say? I'll give him from this corner you go up like this by say maybe 20 centimeters and go like this by 10 centimeters, you get it. It's a ridiculous way of telling it. Instead what I will say is, I fit a coordinate system called XW, where W stands for world, YW, at the corner of the table. I will tell him, the origin of a coordinate system called XW, YW is fitted at this corner of the table, bottom left hand corner. In this coordinate system, this point, the base of the robot is at 10, or 5, 10 centimeters or meters or whatever, right? Then, this is what I would say. This is where the robot. Then he asked me, where is this object? The robot has to fix. With a scale I can measure where the object is, correct? And give him that. Of course, I have to specify a point on the object and tell him it is there. Okay. So this is what I can do. Then I tell him you go and bring a measuring tape and then measure all these things, and the robot of course base. So it makes sense to find out where the robot base is by using a measuring tape or looking at the drawing based on which the robot has been fixed to the table. It makes sense. But objects are transferred here and there. Does it make sense to every time run around, bring a measuring tape and find out the XY coordinates of that object? And still the angle is left out, the orientation. So you will say, I will bring a protractor and measure the angle to get the orientation. Does it make sense? So what do? You have the robot there, use it as a measuring device and find out. Correct? Just bring it up here and find out where the object is. You can capture the X, Y and the orientation. Now, that X, Y orientation which you capture, you will end up essentially, so here is the world and here is the XW, YW. Using the robot as a measuring device, in all probability, you would have captured that information in the X robot, Y robot coordinate frame fitted to the robot base. Am I right? See, you have this link length, this link length, this link length known to you, and through these angles what you work out will essentially be the position of this object in this coordinate frame, the base of the robot. So there is a X world coordinate frame, there is a robot coordinate. Okay. So you will, as you go, then I can fit a coordinate frame to the object also. Job. I will call it a job. Then the inclination of the orientation of this object is the inclination of the X job axis with the X robot axis. So I will paste a paper containing these two axes on the job. So I have that. I will paste the paper on the base of the robot. So this is the robot coordinate, origin of the robot coordinate system, and this is the base coordinate system. That's the, I think I should use the word base rather than robot, because that's the base of the robot, and the world is here. See, in a shop floor, on the table when objects are kept and there is no robot there, you want to install a robot, you want to know where the objects are moving. In all probability, the worker will read drawings and say, he will give you information in which coordinate system, the world or the, he will say that these objects are going to be placed here, here, here. Essentially he is giving you on the table, he is giving you information in the world coordinate system, whereas the robot requires information in the robot coordinate system in order to approach the object, to solve the equations or whatever. Am I right? So there should be a transformation to from this. So we tend to fit several coordinate systems in order to do this exercise. This is known as the terminology of the various coordinate systems. There is another coordinate system which is used, which is what is known as the tool coordinate system. I will just touch upon it as I end this lecture. So here is the base of the robot. I have got a base coordinate system here. X base, I won't use the word robot, I will call it X base, Y base. Remember, this is stuck onto the base of the robot, it doesn't turn or anything. There. Then there is what is known as a tool coordinate system. That is stuck onto this gripper. I will draw the gripper as a plate and show you. Y tool. X tool. And I have my job sitting on the, to which I have fitted one coordinate system called the X job. Correct? Now obviously when I want the gripper, I will show you. These are the gripper's fingers. The gripper's fingers. I have just shown, you know. Now when I want the gripper to grasp the job like this, obviously the which coordinate should align with the X job? The X tool should align with that one, or be parallel to, depending on how you have defined it. And sometimes, you know, for example, in this Titanic, you see in that movie, that submarine going down, and there are two arms, and the whole submarine is going. It is stopped somewhere, that robot, submarine robot. Then it has to operate this lever. The lever is here, and the hand is here. Okay? Essentially what you want is, supposing you are sitting in the hand, you will say, if I go straight ahead, I can grasp the lever. So you are expressing the motion in the tool coordinate system. You are saying that since you are sitting on the gripper, you are sitting, you imagine yourself to be at the origin of the tool coordinate system. You will say, if I go along this axis, the X axis or Y axis, whatever you have defined in that direction, I will go and straight away. So information can be given to the robot in various coordinate systems. When you are cycling, okay, and you are pedaling down the road, when somebody says you have to take a right turn, in which coordinate system is the information being given? Your cycle has to turn orient 90 degrees, turn through 90 degrees. That is in your own tool coordinate. You are the tool coordinate. Go straight ahead. If it is in a world coordinate system, you are on a cycle, or in a car, or in a mobile. You are traveling along a road. In the world coordinate system, the road is of course turning. This is the world. This is a road branching into two directions. In the world coordinate system, there is some angle and all associated. But supposing you are in a car, it is moving in this direction. In your own car system, in the tool coordinate system, as I would call it, you are still moving straight ahead. That's all. Go along this line. So they will say, take a left and then keep moving in the same direction as you see. That's how the information is passing. So there are several types of coordinate systems. The world, you should keep this terminology in your mind as we go ahead. In the more advanced topics, base, tool, each has its own utility. The tool is particularly very useful when you want an object to be gripped and the gripper has approached the object. This is the gripper, it is approaching the object is sitting here. You have come close, then you simply tell it, move ahead. Move ahead means in the tool coordinate system along a particular axis, keep going in that direction. Give that axis. Okay, I think with this I will close today's lecture.